Hey everybody, Mr. Wada here. Just a heads up, I'm going to be doing a bunch of little lessons like this on different topics so that as we go through our distance learning, you have the ability to learn anything that you have missed from the past, and it'll coincide along with the work we're doing in class, so that way you can keep up with the work I'm posting on Classroom. Anyways, so in science, in general, it is extremely important to understand how to make measurements, how to use data, and how to know whether or not data is accurate or not. There's a lot of information going around about things like the coronavirus right now, and being able to sift through all of that data and make sense of it is not only important for you, but I feel like it's important for anyone that you come into contact with. So there's one example, but I have another example for you that I think will, well, at least for many people, they'll remember. So how important is accuracy? So I don't know if you remember this moment, but this is one of my favorite moments in basketball history. That's LeBron James talking to J.R. Smith. And by talking, I mean staring at him like, how could you have done this to me? What is wrong with you? And what happened is J.R. Smith didn't accurately measure the game time. You see, he forgot to check the clock because he thought that he had more time than he had. So he was like running around with the ball, running the wrong way with the ball. And LeBron is like pointing at the hoop like, go, shoot the ball. And he's just pointing at the hoop. And J.R. Smith didn't do anything because he didn't measure the game time. So this is important in places you might not expect, even in basketball. But today we're going to focus on how it's important in chemistry. And we're going to go through a couple examples to learn what accuracy, precision, and error actually all mean. So first up, we're going to be using a couple of different pictures here as a reference. So I'm going to go through part by part, but this is basically precision and accuracy graphed so that we can see what it looks like. And this would be like points on a target, but this is also true for numbers when you measure things, which you'll see in a bit. So first, accuracy. Accuracy is how close your answer is to the correct answer. So basically, you are accurate if you are close to what is correct. That means you can be accurate and not be perfect, which is important to understand. So if you're looking for 10 grams of something, if you make 9.5 grams of it, that's pretty accurate. That's close. That's 95% of the way there. Next up would be precision, and precision is talking about how close your measurements are to each other. So if you notice, the one on the left there says accurate but not precise, and that's because all of the shots there are relatively close to the center, but they are not all close to each other. And then if you look at the one on the right, it is precise and accurate because all of the shots are close together, all the points are close together, and they're all close to the center point there. You can also be precise and not accurate, where all the points are pretty far away. And then error is how far your answer was from the real answer. And we're going to go over how to do that mathematically later. So accuracy is how close your answer is to the correct answer. Precision compares how close your measurements are to each other. And error is how far your answer was from the real answer, or how far your actual measurement was from the expected measurement. So which two of those are opposites? I'm going to give you a second to process that, but which two of those things up there, accuracy, precision, and error, are opposites of each other? Okay, so notice that two of those are referencing the correct or real answer. So that means accuracy and error are in opposition to each other. You can be precise and wrong. You can measure 0 out of 100 a million times, and you are very precise. You got 0 every single time. So all your measurements are close together. It does not mean that you are accurate, though. So the two that are opposite are accuracy and error. The more accurate you are, the less error you have, and the more error you have, the less accurate you were. So another analogy I like is a dartboard, and I think this is the one that works the best for most people, but it shows you these 4 scenarios here. So you've got low accuracy and precision on the left there because nothing is near the bullseye. Your measurements are off and they're not close together. On the next one, your accuracy is low because you're not near the target, you're not near the bullseye, but your precision is high because all of the darts are right next to each other. Next, you have high accuracy. Everything is close to the middle, but low precision because none of the darts are right next to each other. It's kind of hard to demonstrate high accuracy and low precision because normally if you're very accurate, you're also relatively precise. And the last one is high accuracy and precision because everything is in the bullseye. Also, whoever was playing darts there is really good. So, in this picture on the right here, I've got a bunch of different rulers there. And my question to you is, what do you notice about each ruler's ability to make accurate measurements? So take a look at all 3 of those and just really briefly reflect on that. And then my next question is, if you had to make a measurement on all 3 of those bars above the rulers, which of them do you think would be the most accurate? If you answered with C, it means you have a pretty decent understanding because you can't be very accurate if your measurement tools are not precise. Now, I know we're using the word precise slightly differently here, but if you look at the first one, you would imagine that it's 9.5 or something around there, but you have no way of proving that because the measurement tool can't actually tell you 9.5. All it can tell you is 9 and 10. So if you were working in professional science and that was the ruler you had available to you, the best you could do is say, well, 9.5 rounds to 10, so I guess we have 10. If you look at the second one, that is much closer. It's not exactly 8.5, but it's close enough where you would be able to say, okay, that rounds to 8.5. And then if you look at the last one there, you'll notice everything is broken up into fifths. So you would be able to say, well, this is between 11 and 4/5 and 12, which is 11 and 5/5. So you would say, okay, well, that looks like it rounds up to 12. Notice the measurements for the ruler on C give you the most accurate measurements. So the more specific your measurement tool is, the more accurate you can measure things. And then the last thing I wanted to talk about today is the idea of percent error. There's another formula called percent yield, which would be more useful if we were doing labs, but it allows you to look at how much you got compared to what you expected to get. So if you expected 10 grams and you only got 8, you got 80% yield because that's 80% of what you expected to get. But we're more concerned about error. So both of those are measuring an amount out of an expected total, but percent error is the one that we care about right now. So when you're measuring the mass of 4 products in a lab, so say you were working in a lab that makes the medicine that we just recently found out is good at helping with coronavirus, so hydroxychloroquine, you work in a lab and you're measuring amounts. Your expectation is that when you do this reaction, you're going to get 8 grams of it each time. You do this 4 times. But when you do the reaction, you instead get 5.5 grams, 5 grams, 5.5 grams, and 5 grams again. In that data set, are the numbers precise, accurate, both, or neither? And again, I'm going to give you a sec to try and process that. Okay, so let's take a look at what we've got here. All of those numbers are either 5 or 5.5, which means that those numbers are close together. And you're comparing that to 8, which is what you were supposed to get. You're pretty far off from 8 if you got 5 and 5.5, because that means that you're about 3/8 off every time. That's a lot. That's almost half. 2.5 off of 8 is still a lot. That's around a third. So we would not be accurate because we're very far from the actual amount we're supposed to be getting. but we were pretty precise. All of the amounts you got were about the same. If you were doing an actual experiment and this is the result that you got, what you would find is there was probably one mistake or error that you made, and once you corrected that error, because you had done the exact same thing pretty much every time, you would be able to get a really good result once you figured out what that one error is. And I can tell that because if the measurements that you get are precise, it means you did the same thing each time pretty much. Although they're not accurate, if you found that one error, you could fix it. If the answers you get are not precise, it means that you actually don't know what could have been the problem each time because the numbers are random. And then finally, we're going to get to the end here where we're going to look about how you can calculate this. So I changed the numbers a little bit for the second version of this, just to simplify it, and you'll see how it's simpler in a bit. But like I said before, those numbers are precise, but they're not accurate. The numbers are close together, but they're not close to the target. And then for the final bit here, we're going to try and actually do some calculations here. So if you look at the percent error formula, ABS means absolute value. So it's the absolute value of the expected minus the experimental, meaning the number has to be positive when you're all done. That's what absolute value means. So if you had 100 minus 101, that would give you -1. But in this case, since it's absolute value, your -1 has to be positive, so you get 1. All right, with the numbers that we've got, though, it wouldn't matter anyway. So when we measured the mass of 4 grams instead of 8 grams, what was our percent error? Now, you can probably, without even using the formula, figure out that that's half of what you're supposed to get. So if you only got a yield of 50%, that means you had an error of 50%. When you add up the yield and error together, you should get 100. Unless you get over 100% yield, but we're not talking about that now. We're just going over less. So anyways, we have 4 grams instead of 8. So what's our percent error? So if you look at the formula, that means that we need to, for expected, we were expecting 8. So you would have 8 minus what you got in your experiment, which is what you measured. So that's 4. So you'd have 8 minus 4 over your expected, which is 8. So your percent error right now is the absolute value of 8 grams minus 4 grams divided by 8 grams times 100%. Okay, so if you process that first part, that gives you 4 on the top part of the fraction. So you'd have 4 over 8 now times 100%. And if you do the next step and you put that into a calculator, you'll get 0.5 times 100%, and that would give you 50%. So your percent error is 50% because you got half of what you were supposed to get, and 50% is the same as a half. If you have any questions, feel free to leave a comment. I recognize that learning this way is going to be difficult for many of you, and it's also going to be a new thing for me teaching this way, but feel free to let me know if there's anything you're confused about, and I'll be updating with comments on Google Classroom as we go. Thanks, everybody. Have a good rest of your day.